Okay, so as you can see, I have written the problem. The problem says for a simple harmonic oscillator, the usual annihilation operator is defined as A cap is equals to P operator minus I m omega x operator by 2m h cut omega, where P operator means the momentum operator and x means the position operator. So the three questions are: what are the expectation values of A square and A dagger in the state n, and using the relation A acting on Kate 1, where 1 means the first excited state of a harmonic oscillator, is giving us a 0. That means the ground state with eigenvalue 0. Now we have to show that the wave function of the first excited state and ground state are represented by this differential equation, and where xi is usually m omega by h cut root over x, and m omega h cut can be represented as the alpha also, root over. Now we have to use a trial wave function where psi 0x is given as this form and psi 1x is given as this form, to show that fx can be represented as like this. Okay, so the first part is very easy, I think. So at first, now as we know, the operation of A on n will give me a root n and n minus 1 as a state. So we will get again, if we apply it, then we will get n minus 1 will be commoned out as an eigenvalue. Okay, but as the two different states will be orthogonal to each other, this thing will be 0. So we will get a 0. Okay. Similarly, for the second thing, this A dagger. If A dagger acts on n, we will get the eigenvalue n plus 1 root. Then we will get A and the n plus 1. Okay. Similarly, now if again A acts on n plus 1, we will get n plus 1. So the root will be out and it will be reduced to n minus 1. That means n plus 1 minus 1, that means n. So n, and this will give me 1 because the states are orthonormalized. So I will get n plus 1 as the eigen average value of A and A dagger. So this is our problem A, and after that we have to solve B. For B, let us consider that we have to represent our wave functions in position space at first, because the Kate vectors are like don't need any type of representation. Okay, so we can use this as psi 1x and psi 0x. Okay, I think this is a better option for us. So now if we want to apply the A on 1, that means the psi 1x. So now A can be represented in the position space. So P minus I m omega x acting on psi 1. That will essentially give me psi 0. But now see, as we have represented these things, that the operators in position space, P will just give me minus I h cut del del x, and x in position space is just normally x. So we can write further from here that I am not putting any operator sign here, okay, because in position space x cap is just x. P can be represented as minus I h cut 2m h cut omega root over and a del x. So if I take the psi inside, you will get a del psi 1 del x with minus I m omega 2 h cut psi 1 x is equals to psi 0 as a function of x. You can write it if you want. Okay, but see, it is given that this xi is equals to alpha x. So if I write xi is equals to alpha x, but alpha is just a constant, so I can essentially take the derivative and write dxi equal to alpha dx. So basically dxi dx is equals to alpha. Now they have asked in terms of xi, so we have to replace our derivative from x to xi. So I can write minus I h cut by 2m omega del psi 1 del xi and del xi del x. Just a normal chain rule. If I take the minus I common, then I can write plus m omega h cut is just alpha. See? So alpha by root 2 psi 1 x is equals to psi 0 function of x. Now if I take divide by if I divide I on both sides, then I left with a minus m omega by h cut. So if I divide the whole thing by h cut, then I will left with a simple h cut here and this. Okay, this is 1 by root over 2 alpha into this del xi del x will give me also alpha. So alpha into del psi 1 del xi plus alpha by root 2 psi 1 x is equals to 1 by I psi 0 x. Now minus can be written as I square. Okay, and 1 by I also can be written as minus I. So this alpha will get cancelled out and I can take the root 2 common. So I by root 2. Okay, and now we finally left with del psi 1 del xi plus alpha psi 1 x and alpha psi x alpha, that means our xi. So I can write it as xi is equals to minus psi naught x. So finally we can write del psi 1 del xi plus xi psi 1 is equals to our required value, which is root 2i psi 0. This is the problem B, and we have done it. After that, let us move on to given problem C, which says now I have to put the given values here, and we have to satisfy that fx is equals to root over 2i n xi. So we have nothing to do, we just have to put the value in the given equation. I will say that equation 1, and we will get our desired result. So this is the equation we intend to solve. So now if I take a derivative of this function, we will get as f is just a function of x. So if I want to take the derivative with respect to xi, I cannot take it because it is a function of x. So I have to take in terms of x basically. So I have written it wrong, sorry. Okay, so I have to apply the chain rule here. So as you can see, these exponential terms are on the both side and they get cancelled out. So I can write just simply df dx, and dx dj is just the reciprocal of this thing, so I can write it as 1 by alpha. This 2 and these 2 will get cancelled out, so I will left out with a minus sign here, and there will be a xi. Oh, actually these things get cancelled out, I think. Yes. So this, I don't have this term because they basically cancels out. If this thing gets cancelled out, then let me write it in a fair manner. F of x xi plus xi f of x equal to n. Okay, this gets cancels out, and I will be left with df dx is equals to n and alpha. Okay, something is wrong, I think. Oh, I missed the constant here, root over 2 I didn't write there. Sorry about that. Okay, so n alpha root over 2i. So f will be equals to n alpha root over 2i dx. So I will just get n alpha root over 2i x. Okay, and alpha x will give me xi. So I can write f of x is equals to n root over 2i with a xi. That is the required proof. Okay, I guess you guys have understood this. That's it for today, and we will meet again on the next problem which is not solved on the YouTube. Thank you.